Right. Hi, everyone. So from AMD, I'm actually from the group called A+A Solutions Group, and what we are tasked to do is understand the A+A hardware and sort of optimize application tools, scientific applications, so that they can perform and they can efficiently use A+A hardware, so AMD CPUs and GPUs. So as you can see on the title slide itself, you like along with my name, there are a bunch of other names of people from my group who've contributed to this set of slides. And we go out and we are trying to educate people in how they can effectively use AMD ROCm tools to help port their applications, do some development with the new heterogeneous systems which are coming out with A+A hardware. So tonight I'm going to be talking about two main tools that I think are at the crux of all AMD analyzing tools, and those are the rock profiler and the debugger. So going to keep it pretty short, but then the next set of slides are going to be packed with a lot of information. So please feel free to interrupt me if you have any questions. Just feel free to ask in the middle. So up first is profiling, and I'm sure like since morning you've heard a lot about profiling and debugging and using all these kind of tools. So for AMD, the AMD profiler, or as we call it as rocprof, it is the command line front end that you can use to profile on AMD GPUs. It essentially contains all the components that allow you to extract the performance metrics and allow you to do all sort of tracing that you need to understand what your application is doing on the GPU. And rocprof is generally included with ROCm releases for now. And like as our software stack is evolving, you'll see that there are a lot of changes that keep happening in the software stack. So rocprof comes inbuilt into the ROCm releases, and the output from rocprof, like whatever databases that it generates, can be easily visualized using standard browser tools. So like for example, in Chrome browser, you can use the Chrome tracing, or built on top of that is the Perfetto tool that I'll be showcasing today. So you can easily use that to visualize all the traces and all the databases that are generated out of rocprof. So like just to use rocprof, and if you don't know nothing about it, the first thing that you can do is of course use the -h flag. So it will print out the entire use cases of like what all kind of flags that you need to provide to rocprof. But I think there are some special housekeeping flags that I want to bring to your attention, and one of them is the timestamp on. So if you really want to understand the timings of your kernels, you want to have this turned on. It is not turned on by default. So you want to say -- timestamp on or off so that you can see your kernel timings. The second one that I think is very important, especially when you do a lot of templated coding, like say for example, if you're using Cocos and if you're using Raja and things like that, your kernel names can become pretty long and can incorporate a lot of arguments in that. So if you do base names on, it will only give you a shorthand for your kernel name instead of populating with the entire like 2 lines of like the kernel call. So I think these two are pretty useful. And the others that are really required are, for example, where you want the output directory. If not, it is going to dump everything into the temp directory. If you have any data directory, so you can specify that. And if you want to change your temp directory, say for example, you have a lot of people who are working on one remote system, you can also keep, like every user can keep changing their temp directory by giving a temp flag. For tracing, what is important is using different type of tracing modes, the SSH trace, HIP trace, and I'll talk a little more about that. But now say for example, rocprof comes with inbuilt list of hardware counters, but you want to do your own calculation. You can do, like in the advanced usage, you can give a -m flag and you can create your own XML file where you can create your own counters using the basics or the derived counters. So say for example, you want to do the bandwidth calculation, you can combine your reads and writes, and you can divide it by the kernel timing and things like that, and you can come up with a sort of like an approximate of the bandwidth and things like that. So these are, I think, some easy to remember flags that you need to know with rocprof. And say for example, like if you really want to like start getting into it, and I just wanted to throw an example here, like say for example, I want to understand what my GPU code does, like what are the kernels involved in there. So for example, I can just say rocprof --stats base names on, like I said earlier. Now this is going to generate two files because I have the --stats there, and what that is going to do is it's going to generate a statistics which is grouped by each kernel. So instead of having your kernel timings for each call, you'll have grouped statistics, which is pretty important because it sort of highlights what are like the hottest kernels that are consuming most of your time on the GPU. And the code or like the snippet in the middle is sort of giving you an example of that. So you can have more data printed out depending on what flags you're using and things like that. But it is an easy way, and because rocprof is generating a database in the format CSV. Obviously, you can change that as well. But CSV is pretty standard, and you can easily view it, and you can see your kernels and the details. So like I was saying before, that there are different type of tracing that you can do. In rocprof, whether you want to understand about what the HIP API calls are. So when you're doing GPU programming on the AMD ROCm environment, it's all HIP programming languages. So HIP is like a top layer. So if you want to understand what HIP APIs are being used, whether it's the mem copies, whether it's the kernel launches, so you'll use the HIP trace. But if you want to understand a little bit more about what your hardware is doing, you can go to the HSA trace, and you can start extracting things like what HSA calls are being invoked, how are different kernels being queued inside the HSA, and things like that. And I think one thing very useful when you're doing some sort of development and some sort of porting is the roctx marker. So that allows you to inject markers inside your code. So you have to do some sort of code instrumentation, but using that you can profile and you can trace only that portion of the code that you're interested in. So you can do that as well. So an example, like whenever you collect all these traces, there will be a JSON file which will be dumped into your output directory. Now that JSON file is again pretty easy to visualize because, like I said, you can either use the standard browser tracing tools, so like Chrome tracing, or Perfetto. And I'm going to show an example on the next slide of using Perfetto. So say for example, I wanted to collect the HSA and HIP trace. I can open Perfetto, and inside Perfetto, I can see there are three different things. So first of all, I can expand the sections, and I can see the different copies that are happening from device to host and host to device and things like that. The x-axis on the very top is your time, and it displays basically all your counters and things like that. And Perfetto is pretty easy to use. For gamers, it's a heaven. You can use your WASD keyboard, and you can zoom in, zoom out, pan left, pan right, and you can go to the area of your interest. So for example, if you were really interested into one kernel, you can zoom all the way in, and if you click on the bottom right that I've tried to show there, it will open a panel which will give you more information about that kernel. So when you click on that, for example, it will give you again the name of the kernel, what was the timing, how much data was moved, and things like that, on what thread it was being executed, and like all sorts of information. An example of the roctx marker that I was showing earlier was, so on the left-hand side, I've shown some code snippet, and this code you can find on our example GitHub tutorial page. So this is the matrix transfers example. And essentially, when you're inputting, when you're using the roctx markers and you want to inject, say for example, before the kernel launch and after the kernel launch and things like that, and you want to identify those sort of calls, when you do that, and when again you open your trace or the JSON in Perfetto, you have those matching labels right there in the markers and ranges section. So this makes Profiler pretty easy to use, And with that, you can use Profiler on multiple GPUs in a node. You can start extracting a lot of information. And like I said, you can start understanding what your like GPU is doing and like what sort of kernels are being executed. Now, obviously, after understanding your kernels and like what the GPU activity looks like, there comes a point where you want to understand what sort of metrics or like what sort of performance your GPU is giving, and that's where I think the hardware counters are pretty useful. So rocprof comes with two sorts of like predefined hardware counters. So the basic and derived, and you can find them out by using the list basic or list derived flags. And when you want to use them, you can use an input file, and this input file, for example, in the section below, it can be a text file or it can be an XML file. So if you remember from before, I said that if you want to derive and you want to make your own counters using the basic and derived counters, instead of the -i, you can say the -m, and you can give a flag to the XML file of yours. So for example, in my case, if I'm interested in collecting some counters, I have given -i my counters, and my counters basically looks like that. It has a limited number, I've given limited number of counters in each line, which is prefixed by the keyword PMC, and then you prescribe that just by giving spaces. There are no need to provide commas or semicolons and things like that. There is a limited number of counters that you can collect during a specific pass of your application. Obviously, the more counters you want to collect, the more overhead it's going to be, and the more number of passes it will require. So each line in this counter will be collected in one pass. And if you don't know already like what sort of grouping can be done, what you can do is, like in just one line PMC, you can dump all the counters. You can try running rocprof. Obviously, it's going to error out, but along with that error, it's going to give you a suggestion of what sort of groupings are sort of accepted for that hardware. So whether it's MI100 or MI50, and if the hardware counters are changing there, you can try to do those kind of groupings and start understanding. And now again, like I said, a CSV will be created, which will sort of have all the counters and all the requested performance metrics that you really want to know. So all the data will be dumped into a CSV file, and you can change this CSV file into, I think, a DAT file or something like that. I think the most commonly used counters that we have come across and most of our customers are using are listed here. But there is a whole other list of things, and like I said, a lot of people that actually end up making their own counters, because essentially using the basics or the derived counters, you want to understand more important features, like what is your bandwidth, what is your actual occupation, like what sort of arithmetic intensity you're reaching, and things like that. Few tips that I think I want to share with you guys is that when you So every time there is a kernel dispatch, they're all serialized to ensure that only one kernel dispatch is in flight. So make sure that when you're trying to sort of profile your application using rocprof, there are no other, I want to say, stray processes that are running and utilizing that GPU, because otherwise it can really pollute and corrupt your profiling data. I've already said this before. Please make sure you're using base names on, otherwise it can really clutter your CSV files, it can really explode the size of them, and it's really unmanageable to open them. And a lot of people, they've always asked me, how do you identify kernel duration without, doing things like hip tracing and things like that? Like, how do you actually find it out? So, I mean, in rocprof, there is nothing called as like a kernel time and things like that, but with times stamp on, and for whatever counters you're trying to identify, it will always produce like these 4 different times for your kernels, which is basically the dispatch in nanoseconds, at what nanosecond did your kernels begin executing on the GPU, when did it end and when did it complete, basically. So if you just take the difference between the end and begin, that is pretty much very close to your kernel timing, and you can sort of verify that through your hip tracing that I showed before. And then I think one of the important things is a lot of times when you're using these HPC applications, we want to use them on multiple nodes, on multiple servers and things like that, right? Now, at least on a single node, if you're using multiple cores, you can still profile your MPI ranks. So rocprof can collect counters and traces on multiple MPI ranks. So all you have to do is you have to, like, after your MPI executable command, you have to include the rocprof along with its arguments, and then followed by your app arguments. I actually want to make sure that there is an asterisk, and you guys remember this, because previously, like when rocprof was in its early stages, and I think until ROCm 4.5, it used to be the other way around. Like rocprof used to be outside and MPI run used to be inside, but that, and we ended up realizing that we were facing a lot of issues with like multiple streaming, and specifically when multiple MPI ranks are being launched on multiple streams inside a GPU, that was creating a lot of issues with our profiling. So this is a change, and if you try to do the other way around, I think sometimes it works, but it will obviously give you wrong results, and sometimes it errors out, so be careful of that. Multi-node profiling is still not enabled, and it is not supported, because the idea is that when you're trying to develop and when you're trying to do some sort of performance analysis, you can do that on a single node for now. So that is still in the works. We have not rocprof and profiling. You won't be able to get a lot of analysis done on multiple nodes for now. Are there any questions for now before I move on? So I spoke about profiling overheads, and this is a simple estimation based on some example and tutorial cases that I said that exist on our GitHub page. So aggregating all of that, obviously, let me make this remark first, that profiling overhead really depends on what you are trying to do, right? If you want to collect all the counters, obviously it's going to do multiple passes of your application. Obviously it's going to run multiple times, and obviously the overheads might be bigger. But let's say, for example, if you are comparing the HIP trace versus HSA trace, you can obviously see that HSA trace has a bigger overhead as compared to your HIP trace or roctx trace and things like that. And that's because you're trying to tap inside what's happening in the hardware and trying to extract what the queues are doing and things like that. So HSA trace has a bigger overhead, so be aware of that. So that is, in a nutshell, what Roc Profiler can do, Roc Profiler's capabilities and its overheads. The second tool that I want to talk about is the debugger. But before I move on, I want to take a pause and see if you have any questions about rocprof. Yeah?
Does it work for both AMD and NVIDIA GPUs?
So the question is, does rocprof work both for NVIDIA and AMD GPUs? The answer is that HIP as a programming language is designed that you can run it on both on AMD and NVIDIA GPUs. It really depends what you're trying to do. That's what my answer is, because if you're trying to just collect the trace, then yes, it can. But if you're trying to collect the hardware counters, rocprof's, the internal metrics and the hardware counters that are sort of fixed inside it are meant more for AMD side of things. It doesn't have much visibility inside NVIDIA hardware as such. So it really depends on what you're trying to do there. So if you're just trying to collect a trace, it can work, yeah. Yeah.
Do the hardware counters support like the workstation GPUs, or is it only like the data center ones, like the MI200?
That is a good question. So I do want to say that AMD ROCm, they've been trying really hard to come up with a very unified driver system where they can support both the HPC server side of the things and also workstation GPUs. For now, there's only limited support. If you have the newer Navi 2 cards and things like that, only then they have like workstation capabilities. But otherwise, if you have the older AMD GPUs, then unfortunately you will not be able to use it. There are, however, other tools. It's called the GPU Radeon Profiler and things like that, which are already available on AMD website. You can use them for doing more development work on those workstation GPUs. Any? All right, so let's move on. So the second tool, which I think is even more powerful, and for any developer who's really trying to understand how his application is doing, and you know what the performance looks like, and you know where are the bottlenecks and things like that, the debugger is a really handy feature. So the ROCm debugger, or rocgdb, is actually a source level debugger for Linux, and sorry, and it essentially enables heterogeneous debugging on ROCm platform, and it is supported by the AMD debugger API. And I want to say that ROCm GDB is essentially GDB. So it's an initial prototype which focuses on source line debugging, and however, it does not provide any symbolic variable debugging capabilities for now. So it has a lot of nice features, but there are just a few things that are missing. For example, if you really want to do some sort of symbolic debugging. To use the rocgdb, a lot of times the debuggers sort of restrict you to use some sort of optimization levels. But because this is essentially GDB, you can with rocgdb you can use any optimization level. For example, it can be 03 for all you care, or it can be 01, 02. Generally, people use like 02 or O because they really want to understand what's happening in their application. They want to take some time for that, but it really doesn't matter for rocgdb. The most essential flag that you want to enable to be able to do all this kind of debugging is the -ggdb. That's the acronym for like rocgdb. And if you really want to understand, like as you're passing through your kernel launches and you want to see what HIP API calls and everything is are happening, you can optionally print all these useful information by exporting an environment variable, which is the AMD log level, and you can set it to 3. So there are different levels: 0, 1, 2, 3, 4. I think that's the last, but 3 is where you'll see most of the data and like most of the HIP API calls and things like that. So like I said, like because rocgdb is essentially GDB, it has all the features of GDB. So you can like insert breakpoints, you can insert watch points, you can do some assembly level debugging and mapping of the ISR to the source lines. You can switch between different threads and do context switching and understand what's happening there and things like that. And essentially, when we use rocgdb, a lot of our folks, they like to use it with some sort of a graphical user interface. I'm just showcasing 2. I'm sure there are many others that people use, whether it's the TUI or the TUI interface, or whether it's the cursors-based cgdb interface. But the idea is that when you do this when you use them, these kind of front ends, it allows you to have your source code and the console like visible at the same time, and it can do syntax highlighting for you. So as you're passing through your code, it will show you at what line number you are and things like that. So I think this is an essential feature, and especially when you're just starting out with rocgdb and things like that, this can really help you. So I want to like go over and like describe a few features that I said, like for example, inserting breakpoints and things like that. And for people who have not used rocgdb, I think this will be useful. So the first thing is inserting a breakpoint. When you insert a breakpoint, is basically you want to make sure, like when people are developing, you want to see that whether the first section of your code has passed, and am I at that particular line of code or not. So for example, here in in this snapshot that I'm showing. So again, I'm using cgdb, the courses-based debugger. The left-hand side is obviously my source code. The right-hand side is the GDB console. So I want to insert a breakpoint inside my code on line number 40, and that line 40 is basically, and when I say run, you'll see that at line 40 I'll get that syntax highlighting, and it shows me that okay, now you've reached here. So and once you reach there, what you can start doing is that you can start reading or like start seeing like how your variables are initialized, how your pointers are initialized, and things like that, as you can see on the right hand side at the bottom. Now, if you're obviously you're using rocgdb because you want to understand your GPU kernel codes, so you can do that in a device kernel as well. Now, say for example, obviously when you run the command, it starts from your main section, and and GDB doesn't know about the upcoming kernel launch which is going to happen, but you can still insert a breakpoint, and you can call out your kernel. Obviously, at the I don't know if it's visible from there, but you can see that rocgdb is going to spit out a warning saying that, hey, I don't know what kernel name you're trying to call out, but do you still want to go ahead and still want to put a breakpoint there for future? And once you say yes, it's just going to insert that breakpoint, and when you say run or continue, it's going to start running your application till it hits that kernel call, which is basically right there. Now, I think one of the important things is after you've inserted these breakpoints, like say for example, instead of doing command run, which is going to completely run your application, you can also do something which is called as step. So when you do step, it's just going to execute one line of code, and it's going to go step by step and things like that. But when you're doing multi-threading and things like that, what ends up happening is that every time a new thread reaches there, you will see that there will be a context switching which will keep happening. So focus on the bottom three sections. Like on the right hand side, you'll see thread IDs which are different, and each of these threads are hitting the kernel call that I was trying to call. So basically, this context switching is pretty useful if you want to understand like how the occupancy and things like that are varying in your hardware, how many threads are being launched, how many wavefronts are being launched, and things like that. So there's a lot of information in that just one line of code, and basically what it is telling you is that what is the queue ID of that thread, what is the dispatch number, like how many times it has been called already, what is the wave ID, so like what wavefront does that thread belong to, and what block it belongs to, and things like that. So this can be pretty useful, especially when you're trying to debug large codes and when you're trying to understand what's happening inside your GPU kernel, right? The other thing is, other feature is examining your assembly level instructions. Now, assembly level instructions are very useful, and it can give you a lot of insight into your hardware related performance and like how your hardware is behaving. So if your hardware has number of like registers, like how those registers are being filled, if you have some spilling of these registers, obviously you can see those kind of things. So with rocgdb, you can analyze the assembly level language as well. And essentially what you can also do is you can see like where the different threads are residing. Like until now what we have been doing is just doing like hitting step command every now and then, and we've been seeing that different threads like how they propagate. But if you want to see where different threads are residing currently, what piece of the code are they calling and things like that, you can just do info threads, and info thread is going to spit out all the active threads currently, and it will show you their most recent state. And if you want to dive into details about one particular thread, you can always always switch from your existing thread, and you can move on to the next thread and start monitoring that thread's execution. So for that, you have to do thread and the ID number. So for example, right now, the asterisk sign, and maybe I should move, the asterisk sign is on 371. So your current context is what thread 371 is doing. But if you want to switch to thread number 1, all you have to do is just say thread space 1 or T space 1, and that will switch your context, and now you can start seeing what thread 1 is doing. Like I said before, if you do AMD log level 3, and if you really want to get to like even more details about what HIP API calls, what HSA calls are being invoked, you can do AMD log level equal to 3, and you can start running that inside your thread, and you will see that on the right hand side of inside my console, now there is more information which is being dumped, and you will see that all this information is regarding the HIP API calls. Like for example, highlighted in the green, you'll see HIP mallocs and HIP memsets and things like that. So those kind of information is pretty useful, specifically when you want to understand where your HIP API calls are failing you and things like that. So obviously there are a lot of other tips and tricks with rocgdb, and like I said, like context switching and like switching from one thread to the other thread is obviously just one of them, but that's not all. What I've not shown actually in these slides is there is like for example, your code starts failing, right? And you can also do something like go inside GDB, and you can set your pagination to off, you can set your future abort to off and things like that. And when your code fails and it hits that abort, your rocgdb is going to point you to the source code line that it was this particular line that because of which your application basically crashed. So you can identify that why is that crashing. Is it because you're like over prescribing the memory? Is it because you're like doing something wrong which is not supposed to be done and things like that? So GDB, like rock debugger and essentially the GDB interface is pretty handy. It is meant for very serious developers who are trying to understand and trying to extract every juice out of the hardware. So any questions about what rocgdb can do for you? And obviously there's more to it. Like I said, I've not shown a lot of things here. I've tried to contain the information in this 40 minutes of allocated time. But basically you can go online, you can read in the user guide how to use the debugger, how to use the profiler. There are a lot of annotated, like when you download ROCm, inside ROCm as well, like inside rocgdb, you'll have different PDFs which are already in there, packaged inside the ROCm releases, and you can extract those to read about specific features if you are interested in too. And like I said before, rocgdb and rocprofiler are essentially at the crux of all the other tools that are used at AMD, like whether it's the AMD microprof, whether it's the GPU Radeon profiler, because essentially they're going to be using these tools to do all the analysis and show you beautiful plots and things like that. So with that, I think I will call it a day. If there are any questions about AMD tools, just let me know. No questions? Are you guys ready to scale your applications on Frontier already? Okay, good.
I have a quick question. So you guys probably have some experience with the early users for Frontier, right? So do you have any kind of, popular issues on Frontier? Something is not under NDA,
Wait, sorry, can you repeat the question?
So do you have any usual performance bottlenecks you observe from with your
Yeah, so a lot of times what ends up happening, and so Frontier as a system is not just AMD, we are also collaborating with HPE. Now on such a kind of a platform, and especially like I said, when you want to run things at scale, because Frontier is really meant to extract that, like, you know, we got the first exaflops, you're running at scale, you're running at thousands and thousands of nodes and things like that. Making sure that your compiler, your your runtime and everything and all the underlying tools are working in synergy is very important. So I don't want to say that there are bottlenecks, but I think what I want to say is that we are having a really nice strategy, and we are having a really nice collaboration with HPE and their compiler and their tools team, because whenever we want to enable certain features and we want to push out a new ROCm feature, obviously we have this sort of a feedback loop from HPE, because they have most of the front end users, and they tell us that, hey, we want you to have this kind of feature in ROCm tool, and you know, we really want to make sure that we can do things at scale. So they really help us a lot in identifying those kind of features. But one thing which has been troubling us, and one thing which we really are focusing on, is doing multi-node profiling. Like I said in my presentation before, multi-node profiling is not enabled and is not easy to do, and especially when you're now starting to do like exascale type of simulations on Frontier type of systems, you want to understand what is happening at scale. A lot of times your application might scale on a single server or like a single node, but what happens when you start scaling to like 10 nodes, 1,000 nodes? Sometimes you start hitting bottlenecks, your communication starts overlapping and starts taking more chunk of your time and things like that. So getting those things right is important. So I think those are the kind of features we are focusing on.
Yeah, thank you, Suyash.